Welcome back to the Explainer. Last video, we laid the groundwork on neutral point resistor earth networks, and exactly why they exist. Today, we're getting strictly practical. How does the protection system actually act as the eyes of the network to catch a fault in real time? And once it sees it, how does it decide what to shut down? Let's jump right in.
Okay, let's dive into this by briefly tethering back to part 1. You'll remember that a neutral point resistor, or NPR, serves as this deliberate, calculated middle ground. By earthing a generator's star point through a resistor, we limit the fault current to a stable, moderate level. It totally prevents those violent, equipment-destroying current spikes you'd get in a directly earthed system. But it also stops the completely invisible faults you'd get in an isolated network. Here's the catch, though. Because that current is limited and stable, it is inherently way harder to detect. So how does the protection system actually spot a fault happening somewhere deep in the plant? Well, let's start with catching the earth fault through current detection. These are the primary sensors deployed on every feeder and generator. Now, what's really interesting about this is how brilliantly simple the physics actually are. Method 1 relies on the toroidal, or ring, current transformer. The ECTs are physically wrapped right around all three phases of a feeder cable. Under perfectly healthy, normal conditions, the vector sum of the three phases, L1 plus L2 plus L3, equals exactly 0. The currents balance out perfectly within the ring. But if an earth fault hits, that balance is instantly broken. Current is leaking to earth, so it's not returning through the phase conductors. Suddenly, that residual sum doesn't equal 0 anymore. It directly equals the earth fault current itself, which we call IE. The toroidal CT sees this imbalance the millisecond it happens. Moving right along to method 2, catching the earth fault via voltage detection. Because honestly, we don't just rely on watching current. We build a safety net by watching voltage too. So method 2 measures residual voltage, often called U0, taken directly from an open delta voltage transformer right on the bus bar. Normally, just like current, phase voltages naturally sum to 0, but during a fault, they distort. U0 rises according to a very specific mathematical relationship. It's the earth fault current divided by the combined admittance of the NPR resistance and the network's natural ground capacitance. Basically, this gives the system a mathematically verifiable, foolproof way to confirm an active fault. Which brings us to the really critical part, the art of selectivity. Detecting the fault is one thing. Isolating it correctly is a whole different ballgame. And this brilliantly illustrates where true principled engineer skill comes in. Notice the strict rules of isolation across 3 distinct fault locations. We're looking at 3 totally different breaker trip patterns here. If a fault happens inside a generator winding, the system absolutely must trip the generator's neutral point breaker and its main breaker immediately. That isolates just that specific machine. But what if the fault is down a feeder cable? Well, selectivity dictates we trip only that specific feeder breaker. The generators and the main bus bar stay perfectly online, and the ship keeps moving. Finally, if the fault is in an inter-switchboard tie cable, the golden rule is to trip the tie breakers first. Actually, let's do a rapid-fire quick check to put you right in the engine room. Imagine you're standing in front of the main distribution boards. Boom! An earth fault is suddenly detected right in the inter-switchboard tie cable, connecting switchboard 1 and switchboard 2. Alarms are blaring. Based on the rules we just went over, what needs to trip first? So the crucial point is that the tiebreakers trip first, always. By instantly opening the tiebreakers, you effectively sever the faulty cable from both sides. But more importantly, you instantly split the entire power plant into 2 isolated, independently stable grids before a single generator gets taken offline. This maneuver buys the engineering crew critical time to isolate the exact location of the fault without completely blacking out either half of the vessel. It is quite literally a masterclass in system survivability. Let's take a quick second to validate your learning journey across this 2-part explainer. You came into this knowing that NPR earthing existed, but look at your toolkit now. You can mathematically explain exactly how the system detects those faults using toroidal CTs and open delta voltage coils. And, most critically, you can accurately predict the exact breaker trip patterns required to save a plant from a generator fault, a feeder fault, or a tie cable fault. You've officially got a grasp of these complex protection schemes to a principal engineer standard. Huge win. Up to this point, we focused really heavily on plant-wide protection, the entire switchboard and generation network. But what happens when we zoom all the way down to a single critical asset? Next time, we are going to dive deep into the numerical relay that stands guard over individual large motors, the SPM150C. We'll unpack how one tiny aluminum box keeps a massive motor from burning itself to a crisp. But until then, I want to leave you with this. If an NPR limits fault current specifically to save the equipment, what happens if the detection systems we just covered completely fail to see it? Think about that for a bit. Catch you in the next one.